Okay, section 19.3 is on redox titrations. So just a reminder, a titration is an analytical technique where you determine the concentration of an unknown solution by reacting it with some co-reactant who has a very precisely standardized and known concentration. You're able to add, the unknown is called the analyte, and the thing you add is called the titrant. And you're able to add the titrant very slowly and precisely, and you have some sensitivity to the point where the analyte and the titrant have been added in stoichiometric amounts. That means the correct molar ratio for a complete reaction. And so you're sensitive either to the disappearance of analyte as it gets consumed, or maybe the appearance of excess titrant or something like that. We've done acid-base titrations in 1210. Well, you're able to do redox titrations as well. So in redox titrations, you can titrate any reaction with redox reactivity. Identifying the endpoint can be done in one of several ways. You can have titrant or analyte itself, which has a color to it. Permanganate, for example, is an ion MnO4-. Permanganate is an oxidizing agent, and it is purple colored, and it will be reduced to colorless Mn2+ ions. So that makes it a convenient titrant. If you need to oxidize something, use permanganate as your oxidizing agent. And as long as you're adding it and it gets immediately consumed in reaction and turned colorless, then you'll know you haven't reached the endpoint yet. But once you've completely reacted your analyte and you add a drop of permanganate, it will remain purple and you know that you're at the endpoint. You can also use color indicators that are sort of participating in a secondary redox reaction. This is actually what you did in your lab, where you used the triiodide and iodate and starch interactions to use as a color indicator. And so just like acid-base color indicators are kind of a secondary acid-base reaction which is sensitive to the overall acid-base conditions which are governed by the primary reaction. Redox color indicators are a secondary redox reaction that are sensitive to the overall conditions governed by the primary redox reaction you're titrating, and that have different colors on a reactant and product side. That's what makes them useful as an indicator. And then lastly, you could use an electrochemical probe. A pH probe is actually an electrochemical probe, and as long as you've got a voltmeter, a way to record and monitor the electrochemical potential of the solution, then you can use an appropriate electrochemical probe for any redox reaction. And that will give you a nice, smooth titration curve with lots of data, just like pH probes do for acid-base reactions. So one way that redox reactions are different from acid-base reactions is that they will commonly have complex stoichiometry. Acid-base, it's 1 mole of sodium hydroxide for 1 mole of nitric acid. It's a 1-to-1 molar ratio. If you have a multiprotic acid, then you might have multiple equivalence points. So your titration curve will have multiple steep points, but it's still just a 1-to-1 stoichiometric ratio for each segment of the titration curve. With redox reactions, things can get more complicated with respect to stoichiometry. And so I like to solve them, instead of using the titration reaction, to use dimensional analysis and relate the corresponding amounts of your analyte to the amount of your titrant through dimensional analysis. And we'll show you how to do that with an example here. So suppose you have the reaction of 3-methanol plus 2-dichromate plus 16H plus, and I'm obviously running out of room here, so I'll write real small, is going to yield 3CH2O2. That's formic acid plus 4 Cr3 plus 11 H2O. And of course you could be given just the reactants and products in an unbalanced form and asked to balance them. But here we've got a balanced reaction, and the key point here are the stoichiometric coefficients for our two relevant co-reactants. So we have 3CH3OH for every 2 Cr2O7, and that's a 2- ion dichromate. So this is the bridge between our titrant and our analyte. Let me pull up our practice problem. There we go. Here we are. Okay, so if you have a 15 milliliter solution of methanol that is titrated with 7.35 milliliters of 0.0887 molar sodium dichromate solution, according to this reaction, then what is your original methanol concentration? So we're going to start with the measured amount that is specific to this problem, and that is the volume of titrant. So I'll do 7.35 milliliters. And this is a dimensional analysis problem, so we'll draw a big old line there. And the molar concentration of the titrant is 0.0887 moles per liter. So we can say 0.0887 moles of dichromate is in every liter. And you know, the fact that we have milliliters here and liters there is not going to be a problem. You'll see how this will, units will cancel, and it's just simpler if we use that molar concentration without making a direct conversion from milliliters to liters. And I know that 2 Cr2O7 minus 2 minus is 3 CH3OH, and that gives me moles of methanol, and we'll divide that by the initial volume of the methanol, which is 15.00 milliliters. And you see here how the milliliters cancel. Our moles of dichromate cancel, and we're left with moles of methanol per liter. Put that in your calculator, and you're going to end up with 0.0652 moles per liter of methanol in your original unknown. Sorry, let me show it right there. And you will be given another practice problem like this in the quiz, so you can practice with that. But they're pretty straightforward, just a big long dimensional analysis problem, and that's section 19.3.